So, chemical reactions and quantities is where we're at. So, something from last time that we did not get into yet says how many moles of oxygen are required to react with 2.68 moles of nitrogen to form dinitrogen tetraoxide. That should be oxide, not oxygen. Ooh. So, we don't have a chemical reaction given to us in this problem. So, we have to kind of figure that part out. And in doing so, it's going to require us to read the problem multiple times. First off, we got to read the problem as in to try and figure out what are the reactants and what are the products. How many oxygen are required to react with a blank of nitrogen to form? To form is our big indication that that's a product. We're not forming reactants. We're forming products. So dinitrogen tetraoxide is a product. Now the other thing is it requires us to now know our naming of dinitrogen tetraoxide. It formed. It was made by. What was it made by? Well, in a synthesis reaction, there are some kind of dead giveaways. In a synthesis reaction, if it's over here, it has to be over here in some manner. And now we read the problem and say, okay, oxygen reacts with nitrogen. Okay? I'm skipping over things because this part right here, that has nothing to do with the actual chemical reaction. That's talking about moles and stuff like that. Oxygen reacts with nitrogen. So now we say, okay, nitrogen reacts with oxygen. Now the other thing is, something very important is missing. What is it? They're diatomic. H nothing down. Okay? H is in hydrogen, NOF, NOF is in nitrogen, oxygen, fluorine, and then down, chlorine, bromine, and iodine. Okay? That is going to be the one thing. That's a detail that is going to be very important. That's going to get people. Charges and that diatomics is usually kind of a very common mistake, and why we show our work. And if things aren't balancing, double check your charges, double check your diatomics. That would be my suggestion. The balancing of this doesn't take much. Because all we need is 4 oxygen. Now we have enough information where we can go, all right, I think I can kind of start putting some things together. I can start kind of like figuring some things out. How many is usually the question or want, right? How many of moles of oxygen? Okay? That's my want. My given moles of nitrogen. So now we look at these and go, okay, my given 2.68 moles of nitrogen, if I'm going to get rid of something, it would be getting rid of my moles of nitrogen. And I can go and convert 2 moles of oxygen directly, utilizing the ratio that we have them in. How many moles do I have of nitrogen? Well, technically no numbers written there, right? So it means it's 1. How many moles of oxygen? 2. My moles of nitrogen cancel out, just like in a conversion problem. And now I have to put 2.68 times 2. To give me 5.36 moles of oxygen. Now, sometimes people ask, then why did we have to write out the chemical reaction? We had to write out the chemical reaction because that gave us the correct stoichiometric ratio, or the mole-to-mole ratio. That's our conversion factor. Okay? The mole-to-mole ratio, or the conversion factor, also known as the stoichiometric ratio, changes for every chemical reaction. So if we're not given this, we have to find that. If you're going from one thing, converting of one thing to another thing. If we just had, moles of nitrogen to atoms of nitrogen, we wouldn't need the balanced chemical reaction. Could care less about it. Because we're keeping everything in same. If we wanted to find the grams of nitrogen, we could have converted using the molar mass of nitrogen. But when we convert from nitrogen to oxygen, or nitrogen to dinitrogen tetraoxide, then you need that chemical reaction. When you start changing to other things, you need that chemical reaction to happen. Now, we've been building to this point for weeks now. We're ready to solve the lovely experience that chemists do on a day-to-day basis. And in some realities, everybody does. And what you're looking at is how much product will we make if we start with a certain much of reaction. Well, a business is looking at how much of this product do I need to put on my shelf if so and so many people buy it. How many of these bikes do we have to make based on how many people are buying? If I want to double my recipe when making muffins or chocolate chip cookies or monster cookies, Does that mean that I have to double everything or just double the things that I want? And that's kind of what it is. If I want, and sometimes you still like, okay, if I can just double it and you go there, right? Sometimes when you do that, does that guarantee that you're going to double the number of cookies you make? No. You might make bigger cookies than it's prescribed to, so therefore it's going to change that. If you have a set number of outcome, you got to work backwards to figure out how much you need. And that's kind of what stoichiometry is figuring everything out, the what you need and versus what you're given. It's just using chemicals. It becomes the most singular important thing that we've done this year. Everything we have this is like, where are we taking this stuff? It's stoichiometry. It's like, why do we have to learn atoms? Well, you need to know how atoms interact for chemical reactions, which allow us to calculate the correct stoichiometry. Why do we have to know naming? Well, if you don't know naming, you don't know how to balance. You don't know how to balance, you can't get the stoichiometry. Now, and ultimately for the rest of the year, which really isn't much, like 12 weeks or something like that, we're going to utilize stoichiometry the rest of the year. It just becomes little variations of it from it. That's what we basically do. So, we're going to tie together a number of concepts. Writing Bouncy chemical equations, which we kind of almost did. Obtaining molar masses of the needed compounds or the wanted compounds. Converting between mass and moles and vice versa. And converting between moles of one thing and moles of another using the balanced chemical equation. That's just what we did to begin class. The thing is we're doing it all at the same time. And they can feel daunting. Okay? It takes practice. Lots of practice. Because it has a lot of variations in it. You can start with the stoichiometry problem anywhere here and go to any one of these locations over here. When we start here, we're converting to what? Moles. We start with the mass, we want to convert to moles. Starting with a volume, we probably won't get into this one much. I think there's like one or two examples. We just won't get to it in this class this year. You convert to moles. So ultimately it comes down to converting to moles. We're going to add brackets onto this as well as time goes on. If we add something over here, that means we add it in over here as well. Such at the end of the year with thermochemistry, we just add kilojoules per mole. Next is more of a concentration, not paying attention concentration, like how strong something is. That's where that comes from. So there's a lot of different paths. The majority of the ones that we do in my classroom, in this unit, are right there. Those are the most common ones that you will see. That does not mean that your homework in mastering chemistry doesn't have you doing any of the other variations. Okay? Those are just the most common ones. And for this unit, that's what I've chose to focus on, is that pathway. Next unit, we add on that we focus on that one, but that doesn't mean that this pathway can't still happen. It does. Okay? Now, there can be times when we start with moles and we're asked to go to mass, which sometimes, and this is what I see sometimes, people will be given moles and they go, oh, okay, so moles, so I got to convert that to mass, and then they convert it back to moles to go to where they want. That's why paying attention to what you have is so important. It's more important. Okay? And at the end of the year, we really get crazy, and you can actually calculate which one's more energy efficient to heat your house with, propane or natural gas, based on the amount of energy that it comes off from burning of one molecule of it. I know, it gets really... But we'll add volume, we'll add all these other things later. So this is where we're going to focus on for this unit.